Hi everyone and welcome back to PrepFusion. I'm Anish and today we'll start the lecture 3 of power electronics semiconductor devices. So until now we have studied about power diode, we have studied about power transistors. We haven't studied the device physics, but we have studied the working of power transistors and what components are present on power transistors and whatever is required for power electronics side. That much level of device physics we have studied. Everything else is in the prerequisites, or you can refer to the books that I have mentioned. There also you can study if you want to know more. So like the plan was to start SCR, but let's do few important questions on power diodes and power transistors, whatever we studied. So to quickly revise the things, whatever we learned, and to validate whether whatever we have learned is that important for GATE and other examinations or not. So this is the first question. This question came up in GATE 2007. So they have given a circuit which have a AC source, a diode, and a pure inductor L. Okay, so they are asking us that the diode conducts for how much angle. Basically, what is the conduction angle for diode? Basically, for how much period the diode is turned on. So for this, right, first of all you have to understand when will the diode first time turn on, and how long will it turn on. Okay, so if I just do a open circuit test here, if I do open circuit test, this diode will be open circuit. I will assume this diode to be open circuit. Then what I will try to find is when this diode becomes forward biased. So just at t equals to 0 plus, right? This is a sign. Let's assume this as a sinusoid. I don't know peak value. So it can go up to what? It can, let's say at t equals to 0 plus, right? The voltage here is 0.1 volts. Now before t less than 0, right? This circuit wasn't active. I will assume that. So the current, right, this inductor is in steady state. If this inductor is in steady state, then what does that mean? That means the rate of change of current is 0 for this. So the DIL by dt will be 0. Okay, DIL by dt will be 0. So if DIL by dt is 0, I'll just make this more clearer. Okay, sorry for this sneezing. I don't know who is sneezing this bad. So DIL by dt is 0 amperes. Now sorry, not 0, right? Just hold on a second now. Yeah, sorry for the sneezing noise. So as I was explaining, this is 0, right? If this is 0, obviously, like as the inductor is in steady state, obviously the voltage across the inductor initially will be 0, right? So at this point the voltage is 0. At this point I have some positive voltage. So this is anode, this is cathode. So diode will obviously turn on right now. So if diode turns on, what will happen? Whatever the voltage across this, that same voltage will be across the L as well. And diode will be off when? When does a diode become off? When it is turned on? When the current across it is totally 0. So when I is 0, I will say here diode on. When I is 0, diode turns off. Okay, diode turns off. So diode turns off when I is 0 again. So when does it reach 0? For that we have to write the current expression. So if this diode is on, right? If this diode is on, that then what do I know? If the diode is on, that means it is an ideal diode. They haven't mentioned about the like practicality of the diode. So it is like ideally the voltage drop is 0. So what happens is this VL is directly equals to VI, right? So VL equals to VI. Now if we know the voltage, we can find out the current, right? So I know VL equals to LDIL by dt. Okay, so what will be IL? I will start from 0 because before 0 there was nothing in the circuit. So it is 1 by L integration 0 to T VLT dt. And what is VLT dt? It is VI of t. So IL equals to 1 by L Vi of t. Let's assume that it is some Vm sin omega mt. So this will be Vm is a constant, so it will come outside. Integration of 0 to t sine omega t dt. So this will be 1 by omega L minus, it's not 1, here I have Vm as well. Zero to t. Okay, so this is Vm by omega 0 to t. So now what will happen here is that if I write this expression properly, this will be Vm by omega L 1 minus cos omega t. Okay, this will be the expression, because if I put t here, this will be cos omega minus cos omega t. If I put 0, this will be minus 1, and there is a minus sign, like, sorry, this, if I put 0 here and there was, like, this is the lower limit, so minus of minus, this will become plus, so plus 1 will be here. So now they are asking us, when will this diode stop conducting, when will the inductor current hit 0 again? Because at t equals to 0, what do you observe? 1 minus 1 is 0. But when next will it become 0 again? It will become 0 again at omega t equals to 360. Before that, it won't ever be equals to 0. If I draw the graph of this current, right? If I draw the graph of this, so graph of this will look something like this. 1 minus cos omega t is like behaves like this only. This is 0, this will be 2 pi, this will be 4 pi. So at pi by 2, what will happen? At pi by 2, this will be 1. At pi, this will be 2, right? Maximum, because if you put cos pi over here, this will be minus 1. Minus of minus 1 is 1. So 1 plus 1 is 2. So this value will be maximum, that is I max. Okay, and like if you draw the graph next, when it is going to 0, you can equate it with 0. Omega t has to be what? A multiple of, even multiple of pi. Omega t has to be even multiple of pi. On next, it is going off and 2 pi. So the diode is always conducting. The diode is always conducting. So it should be 360 degrees. Because why? Because diode is always conduct. Okay, so that's why answer will be 360 in this case. So it conducts for this whole window, right? 0 to 2 pi. So 2 pi is 360 degrees. So let's now solve this next question. So in this question, right, this is the same type of question only. What they have told is, like, a diode circuit is here and an ideal inductor is here, but instead of closing the switch at t equals to 0, they are closing the switch at t equals to 2.5 milliseconds. All the information is given about the input waveform, about the inductance value, and about the time at which the switch is closed. What are they asking? They are asking the peak value of inductor current. They are asking us this value, right? What will be the peak value? Will it be different this time, or it will be same, like 2 Vm by omega L will it be, or it will be different? For that, we have to find the current expression again. So what is happening is that we will use like the previous analysis only. Just at t equals to 2.5, right? The voltage here is very high. It's like 2.5 milliseconds. That means it is pi by 4. So voltage here is 100 by root 2. Okay, on this end voltage is 100 by root 2. Voltage here is 100 by root 2. And anyways, previously the inductor current was 0 as the switch was open. So obviously if inductor current is 0, there is no change in the inductor current. So obviously the inductor voltage will also be 0, because change in inductor current is 0. Hence this is 0. This is 100 by root 2. So obviously this diode will turn on. So if diode turns on, then what happens is my V L will be equals to Vi, and initial current will obviously be 0. So what will I do? Basically, my IL will be, I will use the same formula, Vm by omega L, integration from 2 this time it will be 2.5 milliseconds, right? I am starting from 2.5 milliseconds, not from 0 to some time t, and this will be sine omega t, that is sine 100 pi t, right? dt. So Vm is 100, omega is some omega, okay, I don't care about that anymore. So this will be, okay, sorry, this is already the value of the integration, so omega won't come here, omega will come later on. So this will be, yeah, cos that, so this will be cos pi by 4 minus cos of 100 pi t. So this is the basically, like, I've derived it in the previous question, so I am not deriving it here again. The same expression I'm using, just it is starting from 2.5 milliseconds. Now what do we have to find? We have to find the maximum current, right? This is the expression for current IL. What will be the maximum value of the current? What is the peak value of current? What I can do is, first of all, I have to understand, before even reaching the maximum value, does it go to this value again, 0 again? If this goes to 0 again, then it won't ever reach the maximum value. So does it reach to 0? We'll see that. So first of all, for finding maxima of any function, what do? We make the derivative 0. So if I make the derivative of this 0, so sine 100 pi t has to be equal to 0, right? What I am doing is making dIL by dt equals to 0. So like I have eliminated the constant, so those I will not write here just to waste time. So dIL by dt equals to 0. So if dIL by dt is equals to 0, if dIL by dt equals to 0, that means that this has to be equal to 0. So this should come later. Okay. So t has to be equals to what? T can be odd multiples of pi. Okay. So t can be odd multiples of pi. So when what is the earliest time? Earliest time is pi only, right? Earliest time is pi. So at pi, this is getting maximum, which is true, right? Because this value is going minimum when this is equals to -1 is the minimum value. So when this is -1, this is overall become maximum, because minus of minus becomes plus. So this one will become +1. So 1 plus cos pi by 4 will be the maxima. Now between pi to pi by 4, right? Between pi to pi by 4, not pi to pi by 4, between t equals to pi by 4 to omega t equals to pi by 4 to omega t equals to pi, is my inductor current going 0? Is it going 0? So we'll observe this, right? So if I observe this here, if I observe this over here, that like omega t, right, at pi by 4 it is plus 1 by root 2. If I just draw the graph of cos, draw the graph, you can put it in a calculator, that's also well and good. So this is cos omega t. So it starts from 1, then it reduces, like at pi by 2, right, it becomes 0, then it goes to negative, right? It goes to negative at pi by 2, then at 3 pi by 4 it goes to minus 1 by root 2, then at pi, okay, it goes to minus 1, then again at 5 pi by 4 it goes to again minus 1 by root 2, and at 3 pi by 2 it goes to 0 again, and at 2 pi it goes to 1 again. So obviously this, right, this thing never goes to plus 1 by root 2. This thing goes to plus 1 by root 2 only here. Okay, so this our inductor current goes to plus 1 by root 2 only at this point, right? After pi, this is the pi value. After pi all this is happening, so I don't care, right? I don't care. My switch like inductor will turn off after this. I don't care about that. I care that, okay, my inductor is always, like my diode is always on after this this pi by 4, and it is still remaining on up until here, but I am getting the peak current, maximum peak current here, because here the cos omega t is minimum and I am taking the negative of that, so it becomes maximum. So Im max or I max will be 100 by omega L. Omega is 100 pi, L is 31.83, it is milli, so 10 cube will go here, and this will be 1 by root 2 plus 1. So the answer to this question will be like all the numbers are very simple, so all the numbers will match here. I will just cross verify this one. So answer to this question will be there was another, okay, one thing I missed out. Is it, or did I miss out anything? 2.5 milliseconds, yeah, fine, this is fine, everything is fine. Milli micro, yeah, I think it is fine. Yeah, I think it is fine. So this is 10 raised to power 5 and divided by 10 raised to power 2, so it becomes 10 cube by pi. Okay, so 10 cube by pi, (31.83). So pi into 31.83 is almost 100. So 100, this becomes 10, right? This becomes 10 into this becomes 1.707. So this becomes 17.07, and approximately 17 amperes will be your answer. This is the value of peak current. Like it will not be this expression, right? This Imax, this will not be same, because here the time at which I am turning off the switch is different. That's why you have to analyze. So it will not be 2 Vm by omega L. It will be 1.707 Vm by omega L. So expressions have changed now. So it all depends at what time you are closing the switch. The conduction angle also depends on that only. Okay, so next few theoretical questions we have. So this is 17 amperes, so this will be 17 amperes, right? Okay, so next this question is there. So a silicon diode is preferred to a germanium diode because of its, due to what? Due to its higher reverse current. Silicon, so it will be preferred. No, if it has higher reverse current, we will not prefer silicon. Lower reverse current, higher reverse breakdown voltage. Higher reverse current and lower reverse breakdown voltage, none of them. So yeah, it is correct. Silicon is preferred because the energy band gap is more. If the energy band gap is more, so that during the reverse bias, right, for electron to go from valence band to conduction band, a lot of energy is required, so the reverse current will be lower. Okay, and obviously it can block higher voltages. As the band gap is more, it can block higher reverse breakdown voltages. So this question came in ESE. So these are theoretical questions mainly come on ESE, right? So I think this is a ESE 2015 question. Now Schottky diode, we have already studied about Schottky diode. Schottky diode is what type of device? A majority carrier device, a minority carrier device, a fast recovery diode, both majority and minority. Obviously both can't happen. Okay, a fast recovery diode, it is a fast diode, but recovery diode, I don't know. Majority or minority? It is a majority, right? Because there is no PN junction. If there is no PN junction, only one type of charge carriers will flow. Okay, so which one of the following is not required for power diode? Which one of the following is not required for power diode? High speed operation, fast communication, small recovery time, low onset voltage drop. So for power diode, right, obviously I don't know fast communication. What is communication? I don't know, right? These are ESE questions. So high speed operation, obviously we want high speed operation. Small recovery time, we want small recovery point. Low onset drop, all these things we want, right? Fast communication, I don't know, does it need to communicate or not? So this will be not required for power diode, right? Okay, so a bipolar junction transistor is used as a power control switch by biasing it in the cutoff region. Okay, so a bipolar junction transistor BJT is used as a power control switch by biasing it in the cutoff region or in the saturation region. So if it is cut off, then it is off. If it is in saturation, then it is on. Then in the on state, the BJT, like what they are talking about, asking us about the junctions. Both the base emitter junction and base collector junctions are reverse bias. Both the base emitter junction reverse bias. This is forward bias. So in during on state, right, the BJT is in saturation. So both the base emitter junction and the base collector junction will be forward bias. So our answer will be here. Both are forward bias. Yeah, option D will be correct in this case. So these are few theoretical questions that you should obviously know. Whatever you have studied, that we are just repeating. Next is this, right? This one figure shows a composite switch consisting of a power transistor in series with a diode. Assuming that the transistor switch and the diode are ideal, the IV characteristics of the composite switch. So basically, like, we haven't studied composite yet, but you can still solve this with basics, right? What are they basically asking? They are asking us the VI characteristics of this overall switch, right? Overall switch. the combination of this BJT and this power diode. Okay, so what do you know about BJT? BJT can block reverse voltage, BJT can block forward voltage as well. All of it depends on the this base current. Can do both these things. Power diode can block reverse voltage, but it cannot block forward voltages. So now, right, I have the power with this, right? It can block the forward voltage as well. If this like this will block all the forward voltage, it doesn't matter about this, so no current will flow. So in this, right, my VI characteristics can be positive and negative as well. It has to be positive and negative. And here, right, in which direction current can flow? Here I have a diode. Diode never allows any reverse current to flow. So only in the positive direction. This is the direction they have shown. Only in this direction current can flow. It cannot flow in the reverse direction. So only in positive direction my current can flow. It can never flow in the reverse direction. So obviously, just with the current, I can safely say the option will be C. But also you can check that in this C option, right, it is blocking the reverse voltage due to this diode and the forward voltage due to the BJT. So both the states are proven here, right? So this is also a similar type of question. So in this question, the figure of a MOSFET is given with the body diode and the on-off states are told with appropriate control. So they are asking the on and off states of the switch are given by VDS and IS plane. Where will the voltage and current like during it when it is on and off, right? So here, right, what do we know? We know about like MOSFET, there is a body diode. So it cannot it is a bidirectional device. It can pass current in both directions due to this body diode. It can block forward voltage, but it cannot block reverse voltage due to the presence of this body diode. So it is a bidirectional device. So current will be in both positive and negative. Here it is in positive, negative. It is only in negative. It is only in positive. So obviously option C will be correct. And you can check from this voltage blocking capability as well that it cannot block any reverse voltage. It can only block forward voltage. So forward voltage is dropped here, blocked here. Sorry, forward voltage is blocked here. I can block forward voltage, but I cannot block reverse voltage. So reverse voltage we cannot block. Okay. Next is this, right? The conduction loss versus device current characteristics of a power MOSFET is best approximated by what? So this is a good question. Basically, what are they asking? Like this is also a gate question, right? This is also a gate question. I don't remember which year this is. So this is also a gate question. Okay. So basically, right, it is asking us about the power as a function of P conduction as a function of current I. Okay, this is what this question is asking us. The conduction loss versus device current characteristics of a power MOSFET is best approximated by what? So it is best approximated. Basically, we can replace our MOSFET, right, when it is on. When it is on, we can replace it with what? A on resistance. RD on. If you remember, we used to replace MOSFET in the when it was in linear region, RD on, right? So here also we can replace our MOSFET with a resistance of RD1. So P conduction will be basically R on into IRMS square into R on. P conduction is equals to I square RMS into R on. So basically, right, here it is the x-axis, this is the y-axis. So if I plot my P conduction with respect to I conduction, basically it will be parabolic in nature, right? It will be parabolic. So it is parabolic. So it will be option A. Okay. In an IGBT cell, the collector and the emitter respectively. So they are asking us about the doping levels of collector and emitter. So if you remember, I will just bring back the figure. But if you know that the emitter, like collector was in the bottom, which was P plus, and emitter was in the top, which was N plus. So I'll just bring back the IGBT structure here so that you will remember here, right? Okay, collector was at the bottom, which was P plus, and emitter was at the top, which was N plus. So like in ESE, right, these type of questions come, just you have to remember the things. So that's the thing for ESE examination. So I will just copy and paste this one. This. So in this case, what we are observing that our collector is here, which with the P plus, and our emitter is with the N plus doping. So collector is P plus and emitter is N plus. So option D will be correct here. Let's solve the third 38th question. This is a good question actually. And ESE, right, they give half baked information, they don't give full information. Like students get confused with this. So first one is, what is the question? The question is, the IGBT insulated gate bipolar transistor used in the circuit has following data. The time required for the switch to turn on is 3 microseconds. The time required for the switch to turn off is 1.2 microseconds. Duty cycle means T on upon T. Okay, so don't worry about this duty cycle. We will study about this in choppers. VCE SAT is 2 volts. So the saturation voltage when the BJT is on, right? When the BJT is on, when the BJT is in saturation region, the voltage across this BJT will be 2 volts, and the switching frequency Fs is equals to 1 kilohertz. What are the switching power losses during turn on and turn off process? So during whatever, first you have to assume, right, during turn on and off, the characteristics, the timing characteristics of the switch is something like this. It is linear. That you have to assume, else you won't be able to do this. They should have mentioned this. They should have drawn the timing characteristics as well. But ESE, they don't do all this. Okay, so but in gate you will get everything. You will get the timing characteristics. Everything will be drawn perfectly. Okay, so here what happens is that when the BJT is on, I can replace this with a voltage source of VCE SAT when the BJT is on. So here, right, when the BJT is trying to turn on, what will happen is it will from VCE SAT, not from VCE SAT, sorry, from what voltage? So initially when there is initially when the BJT is off, right, there is no current across this, no current. So whole VCE will come across this BJT, right? So this will start from 200 volts. This will start from 200 volts. And what will happen when the BJT is fully turned on? When the BJT is fully turned on, this will reach to VCE SAT and stop. The collector to emitter junction voltage cannot increase more than cannot decrease less than 2 volts, right? So what we'll assume is, as 200 is very high, what we'll assume is it almost goes to 0 volts for our simplification, because from 200 to 2 it will be a bit difficult for us to compute. So this almost goes to 0 volts. That is what we'll assume. That is what we'll assume. Okay, next what is it? Next, basically what I can say is, what about the current? So current, right, current is a different thing. So current starts from 0 because there is no switch is off initially, and it turns on. When it turns on, right, totally turns on, the VC SAT is what, 2 volts, and how much current will flow? It will be 200 minus 2 divided by 10 volt, 10. That will be the amount of current. So this will be 198 by 10, right? Then it will reach steady state. The current will not increase any further. So this will be 198 by 10. So current from 0 goes to 198 by 10, and from 200 volt it goes to 0. Okay, assuming 0, it goes to actually 2 volts, but we assume it as 0 volts because 200 is very higher than 0 for our simplified calculations. Now, now you know, right, how to compute the switching losses. I've told you everything. What is this T on? T on is 3 microseconds here. T on is 3 microseconds. So in ESE, you don't have time to derive. You have to use a direct formula. What is the direct formula? If you remember the switching loss formula, I don't recommend though to remember, but obviously once you use this formula in multiple areas, you will easily remember. So the switching loss formula is simply VCE SAT, not VCE, VCE, the maximum value, into ICE divided by 6 into T on into Fs. Fs will obviously be there, right? Fs will obviously be there. So this will be VC is how much? 200 into ICE is how much? 198 divided by 10 divided by 6 into T on. What is T on? T on is 3 microseconds. And what is Fs? Fs is 1 kilohertz. 1 kilo, right? 1 kilohertz. So overall this will become like 600 and this will be 60 by 6. This will be 10 into 198 into 10 raised to power minus 3. So this will be 1.98 watts. So 1.98 watts is in the first option. And what will be the turn off switching. So like we will use the same formula again. Like what will happen in during turn off is that during turning off, right, what will happen, the voltage will increase. During turning off, I will just draw here itself. The voltage will increase and the current will start to decrease. Just one step actually. So it goes to 200 volts again when this is all totally off, right? And the current goes to 0 amps here, and from 198 by 10. So the formula will remain same, and this time the time t off is like t off time is bit lower. It is 1.2 microseconds. Okay, so here this time everything will be same, just it will be lower, right? So this is P switching for on. This is P switching for off. So off again, this will be 200 into 198 divided by 10 into T off. T off is 1.2 micro into 1 kilohertz divided by 6. Okay, so like this becomes this will be the answer will be this, right? This answer will be this basically. So it will be 0.72 0.792 watts. 792 watts. So like you can compute. I already know the answer, so this answer will be 0.792 watts. So like this is a bit half-baked question because they should have mentioned the timing characteristics. If they don't mention the timing characteristics, it will be difficult. But mostly we solve with formulas in ESE, so that's why we use the formula. But in gate this type of question will come, but they will give the timing characteristics. Okay, like more difficult question can come, but they will give the timing characteristics. So let's solve the last question. Last question is this one, that a double pulse measurement for an inductively loaded circuit controlled by IGBT switch is carried out to evaluate the reverse recovery characteristics of the diode D. Reverse recovery characteristics of the diode D. Like a test is carried out, okay, with IGBT, represented approximately as a piecewise linear plot of current versus time. So double pulse measurement for an inductively loaded circuit controlled by IGBT switch is carried out to evaluate the IGBT switch. Okay, this diode is carried out to find the like reverse recovery characteristics for this diode, right? We have to find the reverse recovery characteristics. So now piecewise, like this is linear model. If L bar is a parasitic inductance due to wiring of the circuit and is in series with the diode, okay, the point on the plot by 1 to 3 which at which the IGBT experiences highest current stress. So when will it experience highest current stress? When will a IGBT experience highest current stress? So generally IGBT is a unidirectional device. This just seem like BJT, right? So during forward bias, I don't have any problem of current. Anyways, current is reducing. But in reverse bias, right, whatever the maximum current will be, that will give the IGBT highest current stress. So like there isn't any like theoretical numerical thing here. Just the thing is when the IGBT is receiving maximum negative current, IGBT maximum negative current is basically it gets high stress. That is at what point? At point 3. At point 3 it gets highest stress, right? So this will be 0.3. So answer will be 3, right? Answer. This will be the answer. Okay, so by like that's it basically. In this lecture we just wanted to solve few PYQs of important PYQs of whatever we have learned till now, and from the next lecture we'll study about SCR in full details, and that will be very very important for you. So like do listen to that lectures very carefully. We'll do a lot of questions, and highest weightage from the first chapter is from the SCR. So that is a very very important topic, and I will see you in the next lecture. Thank you for watching.